So you all know Dimitri and I have been working on this for at least a year and a half, maybe 2 years. And one of the things I always felt that was important with the Core One project is not just making the fourth computer, but actually experimenting with hardware computer architectures. So I always believed that in order to run our system, you need custom hardware. You don't have to have custom hardware. You can go buy a board and play with it on almost any FPGA board because it's in System Verilog. But for the optimal performance, which is what I'm going to talk about in this talk, I think you need custom hardware. So that's what I've been working on. So I call this the AI Playground Development Board. And this is a block diagram of it. So this is a brand new circuit board I've been developing over the last 5 months. And this is a block diagram of it. So we have a single FPGA. We have a fourth computer that includes the outer interpreter and compiler on chip. So I would think that this is probably a first in the area of computer chips where it's actually integrated on the integrated circuit. There may be something out there, and one of you guys can bring it up during the Q&A. So it has 64K by 36 bits of SRAM. Now this SRAM chip that I designed around was designed for cache memory on a motherboard. Its access time is 3 nanoseconds. Now, your typical computer to access DDR memory is between, if it's not on the 4K page, can take 80 to 120 nanoseconds. So this thing is going to scream. Because fourth needs so very little memory to run, you can have a very small memory to run it and have plenty of space for a lot of code. So we have a very fast 64K by 36 bits, which, it's a 32-bit computer, so there's 4 bits free. Dimitri wanted a PS2 keyboard because he wanted it to be a fully self-contained computer. So I got a port you plug in a PS2 computer. There's your laptop. You can hook it up with an RS-232 port and then run a terminal program on your laptop. Also included in the board is an ESP32 that'll be running Brad's eForth on it. I also included at the last minute a 12-pin connector where you can plug in a 4-inch diagonal full color touchscreen display. I also added it's a 2 gigabyte by 16. It's a parallel flash, so it's going to be very fast to read and write. It's actually a 25 nanosecond flash, so that's actually faster than DDR if you have a page miss. And there's 125 million by 16 memory, so that's a persistent memory space. You also have an SD card, which you can get, a terabyte or greater SD card, and that's kind of your long-term storage, your hard drive sort of thing. And of course, it's on a teensy-weensy little card, and it's removable. So this is an architecture of a multi-core system. Like I said, the fourth computer has the outer interpreter and compiler. A Core One core does not. A Core One core is simply a fourth engine, like the Shaboom or the RTX 2010, or some of these other fourths like Dr. Ting's fourth. But it is a true 32-bit fourth, as most of the other FPGA based ports are 16 and written in what's called RTL. So Core 1, because we may have some new people on the call, I'll go over a few basic things about what the whole system's about. Core 1 stands for CISC over RISC engine. So what we're talking about today is only the RISC part. CISC is going to come later. Once the fourth computer is completely finished and running, we're going to start implementing artificial intelligence. We're going to steal from other languages, and create new words and new opcodes to support that. That's why CISC over RISC. So the fourth computer is built on a Core 1 core. It's on top of it, includes the on-chip outer interpreter, the on-chip compiler. It's a 32-bit data bus. We have 64K by 30 bits of cache SRAM with a 3 nanosecond access time. Got 128 million 16-bit wide high-speed flash memory that has a 25 nanosecond access time. We have a removable SD card, 115K bit high-speed serial port, and a 4.5-inch 480 by 320 color display. So the idea is you code in high-level system Verilog. It's called behavioral coding versus RTL. RTL is registered transfer logic. So all of the fourth FPGA computers out there use what's called RTL, where the engineer decides, what registers he has and how they talk to each other, and he has to go right down. Every bit has to be, coded into the design. Whereas what we're doing is we're letting the synthesizer build everything. So it won't be quite as fast as an RTL design, but it will be a way easier to change. If we want to change the architecture, it's very easy to change at a very high level. We will create super fast fourth opcodes in System Verilog. So think of System Verilog as being the assembler, like if you were implementing fourth on a microprocessor. And System Verilog is a lot easier to read than assembler. And it's running at the speed of silicon. We have a busy flag that ensures all opcodes will complete, even if they take longer than a clock cycle. So you can build very complex opcodes that span, 3, 4, 10, 100 clock cycles. It doesn't matter. So when an opcode is running, the processor is stalled. Now the processor is running at 250 million, MIPS, million instructions per second. So if you stalled it by 100 clocks, you wouldn't notice it. But the point is that we don't have to worry about timing. One of the biggest problems with RTL designs is you have to really get your timing right. So that's where the bugs come in FPGA design, is timing. Your setup and hold times and your propagation delays have to be, have to meet your clock timing. Very complex opcodes can be implemented, as I said. You could build an opcode to do something like what Brad's words for an OOP. You could literally create your OOP functions there, his words, and even if they take dozens of cycles, it would still be an opcode and it would run, and it would just stall the processor until it's completed. So it makes programming a whole lot easier. Multiple core ones can be instantiated in the FPGA, so it's only limited to the number of LUTs you have. The board that I designed uses an FPGA family where you can go up to 85,000 LUTs, and you could fit 40 core ones on it. Primitive opcodes can execute at 1 clock cycle, which is about 4 nanoseconds with a 250 megahertz clock. And one of the big things the OS is on the chip. Forth is not only a programming language, it is an operating system unto itself. And you basically build the OS up in words, and you can control all the IO of the computer. You don't need an operating system with Forth. Forth usually is the operating system. So we can also claim that the operating system is in the chip. Yeah, so you can see that the total LUTs on the bottom there's about 10,000 K LUTs. The standard FPGA that will be on the board that only costs about $17 has 25,000 LUTs. So you have 15,000 LUTs to play with for your own stuff, and that's a huge amount for an FP, for doing system Verilog stuff. But you can get up to an 85 K LUT machine. So if you want, we want to play nice with our C brothers, right? There's a whole lot of C code out there. That one of the problems that people say, well, I don't want to, where's all your Forth code? Where's all your libraries and all this stuff? Well, you typically have to build it yourself. So one way to fix that, and to bring in a lot of other people into into using the system, is you can literally put a RISC-V core on the FPGA. You have plenty of room to do that. And with the FPGA that I chose, there's 100 free IO lines on the chip left over from our implementation of the Forth computer with its SRAM and flash and all the other interfaces. So you can put either DDR4 or SRAM memory, because RISC has to have its own memory. You can't share it with the Forth computer. It has to be dedicated. So you can go ahead and put DDR4 or SRAM for the RISC-V to use, and then you need a boot ROM also. So you would need you need a flash chip. It could be a serial and SPI type flash chip if you want to save IO pins, or if you want speed, it could be, you could use the same flash chip that I used on the Forth computer. So this is a way to have your cake and eat it too. You can use all the C libraries. It all would run on the RISC-V core, and then the Forth computer would be the master computer. It would run your high-level program, interface to the humans, run the display and that sort of thing. But let's just say that you wanted to experiment with machine learning or something like that, and there's a GitHub, code that you can download. You just download it, compile into the RISC-V, and then have the Forth computer access the data. The RISC-V would do that processing, and the Forth computer would just talk to it over a 32-bit bus, or could even be an internal serial bus. 32-bit bus would not use that much logic, so that would be a very fast interface. So our performance is, so this screen thing, I can't get rid of it. So I want to talk a little bit about the technology of a typical computer and a laptop. You'll see, I'm going to go buy DDR4 memory. I'm going to buy a stick of it. It's 666 megahertz. Wow, that's really fast. Yeah, right. It's not. Main memory. So this is a paper, and there's a link in the bottom there. This was written in 2007. So our systems have gotten faster, which I take into account when I do the calculations. But he talks about the difference, why caches are very effective in speeding up a normal computer. So assume access to main memory takes 200 cycles, and to access the cache takes 15 cycles. Now in the Core 1, it takes 1 clock cycle. running at 250 megahertz, but on your computer, it could take 15 cycles. I'm going to cut to the chase. So at the bottom there, it says the SRAM on the dev board has an access time of 3 nanoseconds. So basically, fourth running on this dev board in theoretically can run 26 times faster than a DDR4 based computer. Now we'll run some benchmarks when we get done. So don't take that number as set in stone as gospel. It's a theoretical number at this point. There's a lot of stuff that goes on when you design a motherboard, and a laptop could be faster than 26 times slower, but we will see. But this is the theoretical. Yeah, so basically, let's see. Okay, so let's talk about the PCI Express bus. So most high-end computers are using PCI Express bus to connect peripherals together. It's 133 megahertz, 64-bit wide device. And the Core 1 is your GPIO pins. There's 100 of them on the board that connect to the daughter board. So that's essentially the same as your PCI Express bus. It's how you communicate to the daughter card. And we're actually can run at 250 megahertz on talking to the daughter card. And here again, it's subject to testing. We may have to throttle that back a little bit, but theoretically, it can actually be twice as fast as PCI Express. So the Core 1 computer goals. We want to be able to microcode fourth programs and words in boot ROM. I'll get into that a little bit later. Core extensions, opcodes can be complex, taking as many cycles to execute as they require. Fourth words can be made, or fourth words are opcodes. Now, when you create a new word, it's not an opcode. If you use a colon definition, it's created in memory. It's not an opcode, but you could make it an opcode if you want to. You can go in there after you test your fourth word on the system. If you want to speed it up, you can make it an opcode. You can go write it in system Verilog and add to the opcode list. And system Verilog should run many times faster than a fourth word. So, it could be 5 or 10 times faster. So when you find a word, and if it's running too slow for you, all you have to do is rewrite it in system Verilog, create an opcode, and then call the opcode. Yeah, Dimitri has made it so you can intermix opcodes and CFAs. CFA is the address of a word in the dictionary. So when you define a new word, you can interchangeably use an opcode or a word defined in the RAM dictionary. These words execute at the speed of silicon, which is 250 million times a second in our case. One of the things, once we get finished with the RISC part of Core, the R in Core, we want to start building a higher level language of natural language machine on top of fourth. And we can steal and borrow high level concepts from other popular language, like struct, for example, in C. That's a nice little thing. You can easily create, structs and create does for you fourth programmers out there. But we could create structs is kind of a very useful concept. So, we would implement something like that in high level and allow you to use the high level language to do that. As FPGA and computer technology grows, like right now we're at 32 bits, by changing one parameter, you can make it a 64-bit machine, you can make it a 16-bit machine, a 128-bit machine. As FPGAs get bigger and cheaper, this system will grow with the FPGA technology. You can network multiple 32-bit fourth engines together over an on-chip network. So you can have interfaces using a single connection or a 32-bit connection. Typically, the way the fourth engines talk to the fourth computer is via 32-bit registers. So you would have an input and an output 32-bit register that the fourth engine would store and retrieve data from to talk to individual cores over the network. This, I think, one of the problems with the GA144 is there's so much limitation. Talking from one of the F18 processors to like the third one down, you have to go through the one in the middle. So you won't have to do that with this. You can store source code in Flash or disk and compile it on the fly as needed. You can update running programs with new words on the fly. So Brad's previous talk about deferred words. So if you make a deferred word in our system, you can compile the new word, because the compiler actually is executing in parallel with the machine. You can execute and then, you can compile and then in one clock cycle switch to the new code. And this will be really, really important in space-based systems. I've done a lot of space computer work, and I ask every C programmer in the space community, I say, if you have 100 robots that are operating out at Pluto with a low-speed data link that's about 3 kilohertz, and you have to update the software by sending up this huge, multi-megabyte binary blob to 100 robots, how do you solve that problem? I either get a laugh, a chuckle, or they said, I don't know. Well, if they had a Core 1 up there, you would send, the 100 characters of source code or 200 characters of source code, just have it compile right on the machine. That's something C can't do. So this is the architecture of a basic Core 1 engine. It's called a core in FPGA speak. And basically, the opcodes are defined in it. We have an execution engine that executes the opcodes. The program can be micro-coded in boot ROM, and it would typically fourth needs very little RAM. So you might have 1 or 2K or 500 words, which is a 32-bit wide cell, I should say, dedicated to each one of these things. And so you would have that. That's kind of scratch pad memory. The program would execute out of boot ROM, not out of RAM. So you can put as many of these on the chip as you can fit. This engine probably somewhere around 1,500 to 2,000 KLETs. So if you wanted to build a massively parallel computer, you can. So here's an example of what you could build. On the lower left, I say 25 KLET FPGA. So that's a $17 part, and you could put 10 32-bit Core 1s inside of it, doing whatever it is you want, probably managing some sort of peripheral. If you got the 85 KLET version, which is about $45, you could put up to 40 cores in a single FPGA. So when I get the boards done, and after I get them all debugged and running using the 25 KLET FPGA, I could, if there was an interest, I could run a batch of boards with the 85 KLET FPGA and, let your mind go crazy on what kind of parallel applications you want to work on. So The playground development board has an ESP32 for Wi-Fi and Bluetooth, and like I said, it will be running Brad's E4th on it, or ESP4th. This allows access to both the phone and the internet. It's a 32-bit computer unto its own with over 400K of main memory. Very powerful little computer. Actually, it's a dual core. Brad has written everything, his whole forth in C. So there is an opportunity to, extend that forth, adding some other C libraries, for example, into it. But mainly what I'm looking at using it for is to talk to the internet. Because one of the things I want to be able to do on this AI playground development board is talking to chat GPT, and you could just, there'll be a special fourth word that you can instigate a chat with it. So we're using a powerful, it's a LFE5UN25F. It has the most IO pins on it. It's a BGA, and boy, it was something else to lay out the circuit board for that guy to escape all those pins. It also has Arduino Shield compatible connectors on it. So there's a ton of shields out there that you can just plug it on the top and start playing around with it. There's motor shields, there's stereo audio shields, all kinds of stuff. So you can start playing with this thing with all kinds of different hardware without doing any design work. There's 100 extra FPGA pins to snap a daughter card on. Now, this is basically the first daughter card that I designed. It's going to be the Whiskers 2 board, which I've designed, and not for this. I was designing a standalone version, so I'm basically going to bring it over so that it runs on this. So the this board would make such a smart personal robot. It would be unbelievable. So that first application we want to work on is an intelligent personal robot. Super high-speed SerDes based. So FPGAs have a really high serial pins on them, both transmit and receive. It's kind of like a RS-232, but they can transfer in the gigahertz range. So I took a micro USB and put one on the input and one on the output, so you can literally daisy chain these AI playground ports together and build a computer of whatever size you want. You want to hook up 100 boards, you could do it. Has a PS2 keyboard, 4.5-inch, 480 by 320 color LCD touchscreen. Got the SRAM and the 2 gigabit flash memory, as I talked about, and the SD card. So here's the board, and I spent about 5 months, pretty much full time on this board. I've been out of work. Hopefully I'll be working next week at Goddard, NASA Goddard. But anyway, this has been quite a, it's one of those projects that you get this idea, you start it, and you got to finish it, but it's a lot more complex. So these pins here are actually the plug-in for the display card, and I added these a couple weeks ago. So you just snap in the display card. These are your Arduino. You can see my cursor, right? These are the Arduino Shield connectors. These two rows here and here are for the daughter card, and the pins come out underneath of the board. This is also for the daughter card. You got the ESP32 is over here. This notch is in the board because the ESP32 antenna really doesn't want to see a PC board. It would attenuate the signal, so I put a notch in it. So this is that was all the layers. This is only the top side layer. You can see the ESP32 over here. This is your SRAM. Now, the BGA, you can see the little holes here. The BGA is right underneath it. Because the access speed is 3 nanoseconds, you have to keep the traces really short. So by mounting, this is a trick I did on the Archinaut 1 flight computer. I did the same thing. So keep the traces really short. So the traces are really, really short. This is your flash right here. This is one of your USBs, and this is your ESP32 USB. So I did duplicate the serial circuitry for the ESP32. So it is a standalone computer. You plug this cable in, and you can use the Arduino programming interface. And then one of these is for the basically the JTAG or the FPGA. This is your two RS-232 ports up here. Let's see. So that's top side board. This is the bottom side of the board. So this is your FPGA here, and neat thing of. So you get the power supplies and stuff, or just your switching power supplies. It should be very efficient. Here's a 3D rendering of the board, and you can see the Arduino shield connectors here. This is your display connector. This should be a female connector, not a male connector. And then these are your daughter card connectors, and they should be mounted on the bottom side of the board. And there's a picture of the board. This is the bottom side. There's a 3D picture of the board. It's a 6-layer board, by the way. I had to have 6 layers to escape all of those FPGA pins, and I barely had enough layers. 6 makes it not as expensive. As soon as you go up to 8, the price of making the board goes up quite a bit. So Dimitri and I, as you all know, we're very interested in artificial intelligence, and we have a lot of future goals in the area of AI. So expert case-based systems, we're going to put the Triune OS multitasking architecture that I designed on Whiskers on the board. It's easy to implement and steal functions from other languages. Dimitri has already written a prologue for the Core 1. What he's thinking of is only, there's about 7 basic functions in prologue. He's thinking about just making those 7 functions, opcodes, or maybe just a word, maybe word extensions to the language. You can do this with any language. You could, if Smalltalk had some really cool language functions, you could implement them, of course. I wrote a neural network language, which could be implemented. We definitely want a natural language interface. The board uses a serial interface anyway, so that's just like chatting. You're essentially chatting to the computer, just like you're chatting to chat GTP. ML, machine learning can be implemented. We are going to, Brad is going to implement an interface to chat GDP. He volunteered. We can do vector computation type stuff too. So, like I said, we can support communicating with ChatGDP. So here's an example. We'd have a word called chat, quote, space, and you would give a string, like tell me about AI and robotics, which I actually put that in. This is a real response from ChatGDP. Now, he didn't know of the Facebook page, but he did. What he came back with is exactly what we're doing over in AI and robotics anyway. So I thought it was very good. But this is a real message from that computer. The next word's going to implement our create, does, variable, constant, store, and fetch. We would like to build in some local variables. We'll probably do that in the beginning, just using registers. Registers are super cheap in FPGAs. So we'll probably just make them registers in the beginning, but later on, we could look at true local variables. We need to implement loops. Now we've implemented branch and zero branch. Those are already opcodes. So Dimitri has demonstrated branching, but we will be adding the higher level words to the language. So it's going to support my triune operating system, which mimics the human brain, the way that the human brain works. So instincts is like if your finger touches something hot, there's motor sensor fusion in your arm. It'll instinctively pull your arm away before you even think about it. So that's the way the instinct levels works in the triune OS, which is designed for intelligent robots. The other thing is behaviors and tasks. So what you do is you find, and this is where the flag in our processor comes in. You could have a behavior that stops execution of the engine and deals with the situation stops execution in the robot and executes some sort of behavior. You can also add tasks to the task list. You put them in the beginning. The task list runs the way I did it in Whiskers, it runs about 100 hertz. The instinct level is implemented in silicon. So that's your silicon system Verilog code that runs your peripherals are all at the instinct level. And then the goals in learning is your foreground task, which is running, in the RAM and the fourth computer. So here's just cerebral cortex is the outer layer of the brain, folds under the skull, your decision-making, analysis, and dreaming. Limbic system, the gray matter found in the center of the brain, hunger, fear, feelings, fight or flight, that kind of thing. Brainstem is the base of your brain connected to the spinal cord and nervous system, controls critical responses and instinctive behavior. So here's what the multitasking triune OS looks like from a processing point of view. The dashed line is demarcates between this is your foreground and this is your background tasks. So the path forward, long range goals. So I'm going to be bringing up the board. I have about 20 unrouted lines in the board, and right now it's very tedious because every line I want to connect, I have to move 20 or 30 lines around to make room. It's so packed on there. I'll show you the board in a minute. Please join us on AI and Robotics group on Facebook. I will put the link in the chat. Here is actually the link, but I'll put it in the chat so it's easy for you. We are encouraging all people, not just fourth people. So we're gonna have C people, we're gonna have Java people, all these people. We're encouraging them to join our AI and Robotics group, and they can talk about doing ML and C. That's all perfectly fine and encouraged, but we're also going to be bringing up forth and how forth could be used. So this is a way for fourth people to help promote forth in the general programming community by joining this group. It was closed and I wasn't active in trying to find people to join the group, but the Facebook search engine found us and started recommending us to a lot of people, and we're up to about 200 people right now. We probably added 50 people in the last month. So I encourage you to promote the group and to join the group. we'll be implementing the Triune OS multitasking engine going forward is one of the next things on the list. String and array extension words or vectors. A little bit, and further down the road is Prolog and other AI extensions. And we're going to be finishing up the 4th computer system in Verilog code. So this is an example of where we'd like to wind up so that people, I know it doesn't look like 4th, and some of you 4th purists will go, ah, but this is easy to read and easy to program. Think about promoting this in universities and even high schools. So this is where, 4th can evolve into every man's programming language. It's still 4th, we're doing colon definitions, but we can make it a more syntactically easier to read. And I've already talked, Dimitri, and I've talked about this extensively. We know we can do this, so it will be coming down the road, but it's kind of a longer term goal. So this is an example of 4th code that's going to add 2 numbers together and multiply it. So somebody who has never seen 4th before, can you tell me what this does? Well, this is what it does. So this would be, so we're talking about version 1 of locals. What we would do is we'll have a register word, and you can define registers, you can name registers, and then you could say 9 X register store, 12 Y register store, add mult. So this would still be used in RPN. So XY plus Z times result. It's more readable than the previous one. See, that's very readable. This gets rid of a lot of stack manipulation, and FPGAs are register rich. You could have hundreds of registers. They don't cost much. So it's easy for us to do this. It makes code a little easier for newbies to read. So the personal robot daughter board, this is what I'm going to be putting on it. I'm going to put 2 DC motor drivers, so you could drive maybe, I don't know, for 1 to 5 amp DC motors. We'll see when I get down to actually doing it. I want to add 6 servo motor channels, so that the servos that are in model airplanes, you can articulate things on the robot. You could have up to 6 of these hobby motors that you can control. You might make an arm, or you might make a bunch of automated stuff. You might make yourself a head that looks like Robbie the robot or something. It'll have one microphone. It might have more than one, actually, because then we could use it for sound location. It's going to have a pair of stereos. It's going to have stereo speakers, 6 channels of optical sensors like I have on Whiskers. They are really cheap and they work really well. So you can actually make arrays of these optical sensors, like you'll see on the advanced Whiskers robot I have a picture of in a minute. There'll be at least two sonar transducer channels, maybe 4 tactical inputs. It'll have GPS on it. It'll have an initial guidance sensor, which includes compass, magnetometer, and accelerometer. And I'm thinking of a mechanical electrical arm attachment point. So this is a robot that I built and I sold dozens of when I had Angelus Research. It had 2 computers in it, one in the base using the Whiskers board, and one in the head. And so the head was completely autonomous to the base and could be looking around. It had sonar in it. It could see 20 feet away and it could find the doorway. I designed my own custom sonar circuit and it worked really well. It could find doorways really easily. So I'm thinking something like this as the first personal robot. Um, you know, to promote the system, um, a personal robot would be ideal for this. Something that people could play with. So I'm thinking something along these lines. So you could do interactive chatting, natural language, have the Triune OS. It'll be fully autonomous. It's connected to the internet, Bluetooth. This thing could run around your house, be your surveillance robot at night. It'll have cameras, maybe one or two video cameras in it, probably one video camera. It'll do real-time collision avoidance, voice recognition down the road. It could be used for nighttime security. It has I monitor the current going through the motors and the wheels, and I have a circuit that works really well. Whiskers could actually detect when he went from a hard surface to a carpet, and he could react. He could do some behavior based on that. So conclusion, we're going to build a new, easy to use computer for everyone. There's a lot of people that tried to learn C++, and it was just too complicated, and they gave up programming. One of my favorite podcasters is Lex Friedman, and he had a physicist on there that went into quantum computing. I think that was him. Anyway, he said he started to take computer science and he hated programming, using C++, and got into, something else, got into physics instead. So there's definitely people out there that would like a more natural language, conversational type language for programming. And there's all, how many C programmers are there versus the whole population? So we're going after, everybody that just wants to, use a computer like Star Trek, right? When you talk to the computer. So as our first thing, we'll build the next generation AI personal robot. That'll be a lot of people would love to have an AI personal robot pet. The board and the whole system is a powerful way to explore AI and robotics. It's an easy way to learn FPGA technology. You don't have to learn all the synthesis and the model sim, the simulation tools and all that stuff. You can create a little tiny piece of system Verilog code, make it an opcode, and interactively test it. And it'll make developing FPGA code way easier than the way when just using their tools. Explore parallel computing. Universities, students can explore novel computer architectures. Like I said, you can change the different memories, and you can make a different circuit board and explore hardware, brand new hardware ideas, architectures, and concepts. So that's my presentation. Is there any questions?
Yeah, well, I have some comments there, Don. One was, I don't know if you remember, but I was attempting to write a program that inputs C code and then will output the equivalent fourth code. Okay. And also, when you talk about somebody trying to learn C++ and how they hated it, I had that same problem because I would get these weird errors that I didn't know. But when I learned object-oriented programming, which consists of analysis, design, and implementation, then all of a sudden those error codes started making sense. And then I understood what C++ was all about. But going back to the C, the fourth translator, somebody out there suggested, why not use LLVM, or what is it? Of course, I forgot what the name of the corresponding compiler is. But I looked at some of the stuff how to do it, and boy, is it a bear. And the problem with it is it assumes that you're using registers. Well, most silicon engines, that's what they're based off. You have a set of registers, and that's how they work. Forth is different. Now, if you look at G-Forth, it has a data stack, a return stack, floating point stack, or a local stack, and a floating point stack.
It's easy to add those to our system. All of that. Yeah.
Yeah, that's what I'm saying. That's what I'm saying. And if I could just go back and start analyzing the code to the point where it doesn't try to translate things into registers, then and just give me what the operand and op codes are, then I should be able to pull that off, which means my whole goal here was I wanted to be able to take the various real-time operating systems out there and translate into Forth, which in theory should run much faster than C. Because as you know, with a C function, there's a preamble which sets up the stack, there's the code that you want to execute, then there's the post arrow which gets rid of all the stuff and be able to return a value. So
the way you effectively use an FPGA in an embedded system is you write the device driver for each device in system Verilog, and then it updates an input and an output register that is memory mapped to the internal bus that's inside the chip that attaches to the processor. You know, it could be RISC-V or it could be R-Core. So that basically all your interfaces are running in parallel, and only the data going back and forth is registered. And that means that every peripheral that you attach to it is being updated by a 250 megahertz custom little tiny processor that's customized to talking to that interface. So you don't need a real-time operating system. This is so much more real-time than any real-time operating system out there. I mean, by a factor of 100 or even more.
Okay, that makes sense. I really like that. So that you can write code in Forth and just get to your peripherals and do what you need to do. Because in a real-time operating system, or just real-time in period, it has to, be spikes, okay, in processing time. Because I remember working at JPL, they were saying, okay, we want to make sure that all our processors are constantly running. We want to have this, large, where it says I'm running it, this processing system is running at 99%. And I'm going, that really sucks on the tip. You think about it, but the idea of what you said, you do have a real-time operating system, so you can write separate tasks that do whatever you have to do, then that would be really nice. Because when you're putting, you might want to be able to try to write a cracker program that, finds a password. Okay. Well, yours, God, that thing is running lightning quick.
Yeah, I expect it to be way faster than the fastest computer, because Forth is so efficient and needs so little memory to run. It can run directly out of cache.
Exactly.
And we had another question in the comments. Does the FPGA are using digital signal processing facilities? It has everything that you can imagine. That is, so what I'm trying to say is, the DSP functions, you can go out on GitHub and find system Verilog code, and you can add it to your Core 1 source code, and you can create opcodes for the different functions of the DSP, and then they became actual words that you can execute just on your terminal, right? And you can incorporate them in your Forth programming. So there's a ton of system Verilog code out there to do all kinds of stuff from machine learning that you can easily incorporate. One of the neat things about using behavioral Verilog like we did, it's so easy to add code like that to it. Whereas if it's RTL, it really is. It's just not. It's when you write something in RTL code, it's you can't change it very easily, and especially if you're not the person that actually designed it, and you're trying to reverse engineer what the guy's doing. So the system Verilog code. And why don't I'm going to answer a couple more questions here, and then how about if I jump in and I show you a quick the schematics and especially the schematics, because I have something I want to show Brad. Which DSP function does a person want? I have no idea, but whatever you come up with, you can do.
We're going to
C++.
stop the recorder about noon.
What's that?
We're going to want to stop the recorder about noon.
Oh, that's fine. Okay, well, let me do a very quickie. Because I really want to show Brad something here. So there's a thing called reconfigurable computing. And Brad said, oh, it'd be so cool if we could do that. So let's see. Right here. Come on. Come on, zoom to. Oh, there it is. Okay. So the ESP32 has an SPI port on it, and the FPGA is programmed using an SPI port. So with these reconfigurable 0-ohm resistors, I can give Brad a board where he can reprogram the FPGA from code that's running on the ESP32. And I'm going to give Brad one of these boards set up that way. And thanks for volunteering, Brad. Oh, I love it. So what Brad and I were talking about with this is pretty awesome. It turns out you can incrementally configure an FPGA. How about that? So think of in terms of at some point in the future, this is way in the future, that you write a fourth code and we build a fourth to basically FPGA configuration translator, and then it adds to the circuit. You remember at fourth day last year, Chuck Moore said, I asked him specifically, have you ever thought about using the FPGA and playing around with your fourth processor? He says no, because they won't let me design it in my tools, which is fourth. Well, if we created something like that, even Chuck might be interested. So yeah, this is a schematic of the whole thing. These are the power supplies. This is one of the serial
if you're showing your screen, we're not seeing your.
Oh shoot. Where am I?
Okay, my apologies. I'm going to have to go pretty soon. I propose to let the recorder run for another appropriate. That would be Brad.
Yeah, we could curtail it. Don, do you want to have this recorded, or we could curtail it sooner even if you wanted, and just have a conversation, but.
Okay, I just want to ask the audience, are you interested in looking at the source code now, or you have seen it before?
Yes,
You are?
yes.
Okay. Okay, let's keep it running then. If you have any C experience at all, it's gonna look very familiar to you, but different. So this is a system Verilog code. It is about 850 lines of code. So you have a parameter, the database width. If you want to make this 128 bits, just change that to 128. And the whole thing will synthesize. You use a bunch of more LUTs. I have a SPI half implemented. I got the transmitting done. So these are, okay, we're using enum, and these are all the different opcodes. Now we haven't implemented all these. These are proposed opcodes. We're actually going to strip them down and to save some LUTs, but execute is implemented. For example, you got arithmetic, but this is how you design an opcode. Just if you say my opcode, comma, you just added an opcode. You didn't add the functionality, but you did add the name, and then I'll show you where you would add the functionality. So we designed the fourth processor. This is in System Verilog, you have a module that means it's going to be a circuit. And then this defines the interfaces. There's some global registers. There's the interfaces, the input and output. And
You got a question on the chat, Don, about whether the source code is published.
yeah, it's on GitHub. And this code, we're still working on it. So, you know, it's you can actually you can buy a $30 board and download it. It's you probably should give us a few weeks before it's easier, you know, the easiest to load on something, but I will put a link in there on for the GitHub code. You can at least, it does synthesize, you can download the Lattice Radiant software tool, and we're going to take the entire project and zip it. So I'd wait for that because there's some project settings you have to do also. We're using some of the most advanced features, and I'll go over those in just a second. So so we have circular stacks, and this is Dr. Ting's idea. If you put this comment next to where you're creating a large amount of memory type data, this will force it to use block RAM instead of registers. If you don't put this here, it will create the data stock in registers and use up your LUTs. So this is important if you want to do that. Here's an example that I put in the other day. If we wanted to build local registers, and it only added about 60 LUTs to the whole design. So we have defined a dictionary pointer, a return stack pointer. Let's see. Now use the arrows, be easier. Here's an example of creating a register to access an external thing. So we have a red, green, and blue LEDs. We got two buttons. So these registers would you know, capture where you want them on or off, and then the IO pin would toggle. This is defining your UART. This is your dictionary logic. Dimitri would have to kind of explain some of this to you if you want to dig really deep into it. But this is an example of a boot ROM. So this boot ROM is inside the FPGA. It's not in Flash, it's inside the FPGA. And here it executes and then it branches. So this creates basically a loop. Dimitri would have to explain that to you, but here's an example, for example, of some code written in boot ROM. So you have a literal, and this is a question mark, you put it around quote. This could be a number, a regular number, or it could be a quoted character like that, and that would create a literal, and then you could admit it. So this looks a lot, this is like fourth, right? So you'll notice that because it is very primitive code, we're using branch and obranch. So this is called microcoding. And when you have a core 1 that's sitting off by itself, you would microcode it, would probably be the best way to create a little program that's running some device like your display, for example, that I showed you. What else? So here's the outer interpreter, and Dimitri spent a lot of time. He spent months on this. It's pretty complicated code, but luckily you don't have to mess with it. And I don't recommend you messing with it. So basically he creates a state machine, and there's your idle, and this is your parse state. There's your before link, get link, search state. Dimitri would have to explain that to you. Here's number. That's the number state. But you see, if you look at this code, it looks very much like your C code, right? So you can, if you wanted to say, how does this link work? Well, that's not bad. It's not, even if you weren't a system Verilog coder, you could figure out what's going on. That's the most complicated code, and I don't recommend even touching it. But so here's you can do what's called a task, and a task is kind of like a word in forth. So it's a callable. So system Verilog does not run anything sequentially. It makes circuits. That's what it does. The task is the algorithm is kind of like a sequential machine, but really not. It has to take this and it has to build a circuit. Okay, so but what's nice about it is great for encapsulating complexity. So here's fetching an opcode. The branch address goes to the memory pointer. If busy, we increment. Look how simple that is. You know what, you can tell what that's doing, right? It's not magic. It's magic when it was came from an idea and had to go to code, but now it's easy to see. So here's our execute command. So if we're skipping an operation, which are some reasons for doing that, we test for that. Or otherwise we go into a case, and this is where your opcode action is defined. This is your system Verilog. So you decrement the DP pointer. That's your data stack, and data stack equals data stack DP minus data stack DP plus 1. See how simple that is? That's minus in fourth, and here's plus in fourth, and here's 1 plus in fourth, and here's dupe in fourth. So this is how you create an opcode. You first create the name up in the enum section, and then you create the action down here, and you've just created an opcode. So here's your IO LED opcode. We have an opcode called IO LED, and it basically takes the 3 items off the stack and outputs it to the pins. That's what this does. That's really easy, real simple. See how easy that is? There's your IO button. Here's how literal works. So if you know a little bit of C, you're actually, here's branch right here. You notice the busy flag. This is how we implement the busy flag. If it's busy, every clock cycle, this is going to run. If it's busy, it won't execute anything until the busy flag goes true. So at the end, you always want the busy flag to go through in these things, like right here, busy true. Because EMIT is definitely going to take multiple clock cycles because the RS-232 port is only running at 115 kilohertz, right? So the processor stalls while it's running busy, and when busy terminates, then it keeps processing. So that's the engine. So here's your inner interpreter right here. That was the outer interpreter. That was the most complicated one. The inner interpreter is really simple. So you basically get the code and you call texecute. Remember, texecute was a task. Remember that? So it has multiple statements, but when you use task, you hide complexity, and it's like creating a fourth word. That fourth word hides complexity, doesn't it? And it makes it easy to call that fourth word in more fourth words. So that's pretty much it. The other thing that's important, everything is source code. You can copy paste this on anything, on an Altera, on Xilinx, on Lattice, on Microchip, which used to be Microsemi, because we actually coded our own UART. Normally you'd go in the IP catalog and you would pull out a UART IP, but then you're stuck with their tools as soon as you go to the IP catalog. So we did everything in source code. Yeah, so there's UART. This is
refresh my memory, Don. What's the rationale for having the outer interpreter expressed in System Verilog rather than have it build on top of the inner interpreter?
Well, it is built on top of the inner interpreter, but we did not build it. You could build the outer interpreter in forth code. It would run a lot slower, but it could be done. We chose to put we wanted the whole computer. I mean, this is a fourth computer, not a fourth processor. A fourth processor, just the top level is opcodes, right? And then you still have to write fourth on top of it. Like if you had an RTX 2000, you still have to write fourth for it, right? It's its assembler is fourth opcodes, but you still have to do that conversion. We have created an entire fourth processor inside a chip. And yeah, it took us a lot longer to do that. But an interesting thing is the outer interpreter is running at 250 megahertz. So you could have source code sitting out there and you could have it compile on the fly. You probably wouldn't even notice it getting the source code and compiling it. So it's just something that we wanted to do, and for speed, it makes us very unique in that. So this is, I just put the F83 word set down there just kind of as a reference. Okay, so any questions on the source code?
No, it looks like it makes sense to me, Don.
It's really easy, isn't it? Is there any questions on the schematic?
Ooh.
Okay, so
actually, Don, I had a question. So with the SBI pins, is that going to be? You're saying that that's going to be kind of a jumpered configuration or something where you've got the ESP32 able to talk to the SPI for the FPGA. Is that right?
Correct.
Got it. Got it. Okay.
So these pins go to the FPGA, these pins go to the ESP, and these pins go to the flash memory. So if you remove these 0 ohm resistors and add these, then now the ESP32 can actually configure the FPGA. That would be unbelievable. Now people are doing this, so I'm not saying, you know, it's something new. People are already doing this. Brad's done some research into it. I've done some research into it. But by using our system, and because our system runs on Forth, you know, you could literally write Forth words that configure the FPGA. At some point in the future, it could take us a year to implement that kind of stuff. So
yeah, it's definitely like looking at some of these open source tools that do the synthesis. Like they're maybe not as complex as I suspect whatever Lattice and folks have built up over the years. But the even these tools, you know, a lot of them are it's Python and so on. But like it's quite a bit of code, even though the underlying format for the layout of the FPGA is not that bad. But there's a lot of special casing to it. So it'll be a good trick to do it on the fly. They're doing it, but they're doing it still in the form of an overlay where you build, well, here's, you know, block 1 that you load and then block 2, not sort of something where you're synthesizing and deploying it live. Unfortunately, it looks like they're sort of regular in terms of the layout of some of these, but each one is sort of different and they're not perfectly regular. So
look at this. This is the board layout.
That's a lot of layers, Don.
Yeah, this was pretty crazy, especially down in here. Yeah, if I charged a customer for this job, this is a $50,000 job. Easy.
Oh, you got that right. Oh, by the way, did you run design check on your layout here?
Oh yeah, yeah. That's where I'm at right now. I'm doing DRC right now.
Okay.
Yeah, yeah. That's a must on any printed circuit board. I have 20 unconnected nets, which I'm kind of putting 15 to 20 a day in, because now that the board is so packed with routing that I have to move 20 lines to put 1 line in. But I'll be done in the next couple of days, and then I'll go to the DRC errors and warnings. I'm using KiCad 7, which is amazingly easy and powerful. My last job, I used Altium, which cost $3,000 a year to lease the software. It was a pain in the ass. When you wanted to do something, you had to find some sub menu somewhere, because it is evolved sequentially over 20 years, and it wasn't thought of in the beginning on how the GUI would be, and they just keep adding these things hidden in these sub menus. Whereas KiCad, started from scratch, and the GUI is fantastic. I mean, everything is 1 or 2 clicks away that you'd want. It does what's called smart routing. So it won't let you break a DRC rule when you're routing. It'll move things around. It can even move traces around for you if you click on that option. I don't have that turned on, but because it can kind of make a messy board. So the hardware's done in KiCad. It will be open hardware at some point. I'm going to get it all working, and I'm probably going to do a crowdfunding on this board. This would be a great board even for people that want to put a RISC-V in it and use C and System Verilog or VHDL or whatever. I'd like to I spent a lot of time in this thing, so like to get something out of it. But once I finish with the crowdfunding, it'll be, or at the same time, actually, when I do the crowdfunding, I'll make it open hardware. And then you could take my hardware design and you can create your own stuff, your own robots, make your own products. You know, it's open hardware. Just buy me a cup of coffee.
Well, Don, I noticed the time, and I wonder if there's any objections to ending the recording here. And
Yes.
all right, let me
Wait,
push that button, and
Brad?
then we can continue to chat a minute. Oh, yep. Oh,
Brad,
yes.
I want to ask Don a question. Okay? Or a comment.
Sure.
Can you hear me?
Yeah.
Yeah, okay. You did mention that you had to keep your traces short. Does KiCad have a transmission line
Yes,
option to it?
Yeah, it has a trace tuning option.
Yeah, that's what I'm talking about. Yeah.
Yeah, it
Really
has
important.
differential pair routing. It's amazing. It really is something else. Version 7 just came out earlier this year, like in January, February, and it rivals Altium. It really does, and it's free.
Yeah, that's really nice because when you start getting up into the gigahertz region, especially with USB, was it USB 5 now? You have to make sure that your traces, I believe they have to be tuned to 50 ohms, if I'm not mistaken. I'd have to
Yes.
look at the spec. Yeah.
Yeah,
Okay.
I use that tool for the SerDes, the USB. So I use the differential pair routing on those, and also the clock. I have a 50 megahertz clock. So, and inside the FPGA, you can use what's called a PLL, phase lock loop, and you can bump it up to any frequency you want. So I expect our system to be running about 250 megahertz clock. And when we run some comparisons of, I mean, you could write C code and run it on this would be really great. Is take some formula, some sort of processing, write some C code, and then write it in forth on this board. This board should smoke the laptop by an order of magnitude.
Sounds good.
And
Really, I like your design, Don.
yeah, it's been years working up here. Yeah, so I'm pretty proud of it. It couldn't have done it without Dimitri. He's an awesome system Verilog programmer. This would still be a dream if it wasn't for him. He's really good. He got a new job at he's doing really high level FPGA stuff now. Top stuff. Okay, you want to stop the recording?
All right. Let me push the button.